Welcome to week 2. So last week we had a look at first order differential equations and we saw a couple of techniques for how to solve those. This week we start exploring second order equations. Now this is a huge topic that we could spend an entire course on, but instead we're just going to spend 2 weeks. So this week and next week we'll be looking at second order equations. More than that, we're not going to be looking at just general second order differential equations. We're specifically going to be looking at linear ones. So you remember from last week what that means, I hope. If you don't, go and check it out. And we're going to be even more specific than that. We're mostly going to be looking at constant coefficient second order linear differential equations. Now it might seem like that's very specific, but these kinds of differential equations can model a huge variety of systems. In particular, anything that has vibration or periodicity, which when you get down to it is pretty much everything from atoms all the way up to skyscrapers and the solar system and the galaxy itself. So anytime pretty much you see anything that involves a force in any form, you've got, if you remember, an acceleration, which is a second derivative. And suddenly you've got a second order ordinary differential equation. So these are really useful. Now the two key equations that we're going to have a look at are, and they look very similar. The first one is the forced harmonic oscillator. So if we just have a quick look at that, you'll notice that it has a term that has a second derivative of our u. There's our first derivative term, our term just including u, and it also has a term that just depends on t. So from this we can deduce that this differential equation is non-homogeneous. But the first kind that we're actually going to have a look at looks almost exactly the same, except it's the case where we don't have a term that depends only on t. So we're going to start by looking at the harmonic oscillator, which is given by those three terms, but we're looking at the homogeneous version. And what we're going to find is that we can actually use solutions to the homogeneous differential equation to solve the non-homogeneous version. So that's why we need to do the homogeneous version first. So you might be thinking, okay, can you give an example of a physical situation where you might end up with a forced harmonic oscillator? So one of the key areas where people think about this is, for example, in buildings that have to handle earthquakes. So let's look at a very simplified 2D model of a building. So we're going to assume that we've just got a very simple two-dimensional building. It's got a roof, and we're imagining that the mass of the roof is kind of as a point mass at the center, in between two kind of massless rods that are holding it there. So I agree, not a super practical building, but okay, it's useful for the moment. So we've got our roof that has its mass concentrated at the center, and that's supported by two vertical walls, one on either side. And if we think about this, we've got a kind of an equilibrium position where our building would be if nothing happened, but then if the ground judders or anything like that, then the building might tilt from either side. So we're going to be looking at what happens as the kind of the mass of our roof moves from side to side. So we're looking at displacement from the equilibrium. And you can imagine, if you think what will happen if there's a sudden judder of the earth, then the building's going to sway a bit. And we're going to just do a quick kind of force analysis and see where the second order differential equation that models this comes from. And then your intuition will tell you it presumably we have a solution that is oscillating, that hopefully lies down and stops oscillating. So our goal at the end of these 2 weeks is to be able to solve the differential equation and see that we get something that gives us a decaying oscillation. That's where we're headed. It's going to take us a little while, but we're going to get there. But first we need to do what we always do when we look at a physics problem, which is to look at the forces. Okay, so to start talking about this mathematically, we are going to need some variables and things. So let's start by saying let u of t represent the horizontal displacement of our mass that's representing our roof at time t, and it's going to be the displacement away from equilibrium. So we're imagining that we've got some equilibrium position here, and our roof is swaying on either side of that, and what we're measuring is the displacement away from that zero position. Don't worry at the moment why this strange dashpot thing has appeared. We'll talk about that in a moment. Okay, so we want to think about the forces that are acting on the building, and then specifically on our little mass m, when it's displaced from equilibrium. Well, if you think about the situation, as soon as we're displaced from equilibrium, the first thing that's going to happen is that the forces due to the walls are going to push us back towards equilibrium. So this is a restoring force, and if we think about the magnitude of it, the further away from equilibrium we get, the bigger the force to push back. There's a definite feeling of a kind of a spring force happening here. And that's often what you'll find in these kinds of systems. You have some sort of Hooke's law spring thing happening here. So you'll have a restoring force that opposes the displacement, and the magnitude of that restoring force is proportional to the magnitude of the displacement. Tiny displacement, tiny restoring force, big displacement, big restoring force. How could we write that down? Well, we know how to do this. If we've got a magnitude proportional to the magnitude of displacement, we need a constant of proportionality, so let's call it k, good old spring constant k. We're proportional to the displacement, so we're proportional to u of t. And the key thing is, if our displacement is in a positive direction, the force is going to be exerted in the opposite direction. So we need to have a minus sign over here. Okay, so that deals with the first kind of force that would happen in a situation like this. But there are also frictional forces, generally speaking, within a building, which will also oppose the motion. These are, if you think about the atomic bonds within the fabric that makes up the wall, it's going to oppose being moved. So this gives us a kind of a friction happening, and the faster the movement, the more friction we get. So we've got frictional forces, which are proportional to the speed, because remember friction is proportional to speed, so we've got proportional to the first derivative of our displacement, and again we need a constant of proportionality, and again they're opposing the movement, so we've got a minus sign over here. Often in diagrams where we're trying to show that there is some kind of frictional or damping force, we include what's called a dashpot, which is simply a damper. You can think of it as, I guess, something like a shock absorber. So that's what this is doing in our diagram over here. This is indicating that apart from the fact that we've got the walls, we're kind of putting in this dashpot to talk about the frictional damping. So just like in circuit diagrams, you have little symbols for capacitors and resistors and all of that. When you're drawing force diagrams, this is kind of a shorthand notation. If you put a dashpot in, it means that there is some kind of damping force, some kind of frictional force that is usually proportional to the velocity of motion. Okay, so those are two obvious forces. And then the final one that we want to be able to add in is some force, for example, caused by the earthquake, which is just an external force that acts on the system. And here we can't really say that it's proportional to anything involving our displacement or its velocity. It's just going to be some external force. So the best that we can do is call it an F of t. So I'm just going to say we've got an external force, and that's given by F of t. And this is a simple model. You could add in more forces or go into more detail, but for the moment this will do. So how do we pull it all together? Well, we remember our Newton Newton's second law, I think it is, which says that the sum of the forces acting on a mass will be equal to the mass times the acceleration. But remember that acceleration is the second derivative of displacement. So what we actually have is that the sum of the forces is equal to mass times our u double dashed. And if we add together the three forces that we've got, what we've got is minus k u of t, minus c u dashed of t plus f of t is equal to mu double dashed of t. And suddenly you can see where our second order linear constant coefficient differential equation comes from. With a slight little bit of reorganizing, we get almost this. So we had an f of t here. So if I just rewritten this bit over here, we would have, so I've got mu double dashed of t. So I'm taking my right-hand side, kind of, I'm thinking of it as my left-hand side, taking these two terms, my minus terms over to the other side, except I've switched that around, plus cu dashed of t plus k u of t is all going to be equal to f of t. And that right there is our forced harmonic oscillator. So that's the equation that we'll be solving in week 2, but we're going to start with this simple situation where we don't have an external force. We've just got the other ones. We're looking at the unforced harmonic oscillator, which has f t equal to 0. So we're looking at the homogeneous situation. So we will look at a general way of solving these, but I think that the first thing to do is have a kind of quick discussion about what each of the terms here, or each of the constants is about, and then we're going to look at a specific example. So when talking about the unforced harmonic oscillator, even if it's in a system that doesn't necessarily have a clear mass, like our roof had a clear mass, we usually think of this m as a kind of mass term. We will often refer to the coefficient of the u term itself as the spring coefficient, because it comes from the spring part of the term, and the coefficient of our velocity term will often be referred to as the damping term. So we've got a damping and spring term and a mass term. So these coefficients kind of, and we will talk about different kinds of damping situations, and that these will, so it actually turns out that this damping coefficient here plays a huge role in the kind of solution that we get, whether we get something that oscillates a huge amount or dies out. So we will in fact look at 4 possibilities for damping. We will look at overdamped, we will look at underdamped, and we will look at critically damped. And the final one we will look at is no damping. So these are the possibilities. Now, I haven't specified exactly what I mean by overdamped, underdamped, but it will turn out that we have a very specific meaning for each of those. So we kind of classify each of those cases depending on the relationship between m, our mass, and our damping and our spring. But we'll see what that relationship is in a little bit. So to get going, let's not look at a general case, but let's look at a specific example. So here we've got our m is equal to 1. So here we've got m is equal to 1. Our c is equal to 4, so our damping coefficient is 4, and our spring constant is equal to 3. And to start thinking about how we might tackle this, let's rewrite the equation. So you'll see that all I've done here is I've taken my u of t term over to the left. Now let's think about what we're looking for when we're solving a differential equation like this. We're looking for some function u of t. What does it have to look like? Well, we need to have that when we take its first and second derivatives and add them together, suitably scaled, we end up with some multiple of the original function that we had. So we're looking for a function whose derivatives obviously have to be almost exactly the same as it, maybe with a factor in front, but basically they have to be the same. Do we know any functions whose derivative looks almost exactly like it, barring a factor? Why, yes, we do. So we know that the function e to the some constant times t, when differentiated however many times we like it, is always going to give us some factor times by e to the some constant times t. So this is a good one to guess. So we're going to say, let's try a solution of the form u of t is equal to e to the rt. Now, this is a lot like guessing, but it's also, and you'll see this in a lot of physics and maths, is trying something like this is called using an Ansatz, which is from the German word meaning an approach. So it just sounds fancy, but basically it's a guess. So we're going to assume that this is a solution, but in order to show that it's a solution, we need to make sure that it that fits into our differential equation. So if our u of t that we're positing is a solution, then it must satisfy the equation that we're wanting to solve, which is this one over here. How can we check if it solves it? Well, we're going to substitute it in. So we're going to substitute it to the left-hand side of our equation. So that's this bit over here. And then we're going to check that that left-hand side actually equals 0. So let's take some derivatives. So we have u of t is equal to e to the rt. If we take one derivative, then we're going to get an r coming out, and we've got another e to the rt. And if we take a second derivative, then we're going to get an r squared e to the rt. So if we substitute those, the u and the u dash t and u double dashed, into the left-hand side of our equation, what do we get? Well, we're going to get our u double dashed, so that's r squared e to the rt, plus c times our u prime, and our c here was 4. So we've got plus 4r e to the rt, plus finally 3 e to the rt for our u term. So we can do a little bit of rewriting here. I'm going to take out my common e to the rt, so I've got an r squared plus 4r plus 3 all times e to the rt. So that's the left-hand side. And since the right-hand side is 0, we need that r squared plus 4r plus 3 e to the rt is equal to 0 if our u is going to be a solution. But if you have a look at this equation over here, now e to the rt can never be equal to 0, because even if t is equal to 0, then it's just that term is just 1. So over here, this is never 0. So the only way that we can have our u of t that we've posited being a solution is if this term here, our r squared plus 4r plus 3, is equal to 0. So what we've worked out is that we can certainly have a solution of this form, e to the rt, if the r's meet a particular criterion, and that criterion is that r squared plus 4r plus 3 So we have so if our r squared plus 4r plus 3 is equal to 0, then our u of t equal to e to the rt is a solution. But we can actually go a little bit further. We can find out which values of r this is true, because we know how to solve quadratics. So we need that r squared plus 4r plus 3 equals 0. You can do some factorizing and you'll see that's r plus 3, r plus 1 is equal to 0. So this tells us that if r is equal to minus 3 or r is equal to minus 1, then u of t is equal to e to the rt is a solution. So putting that together, we have in fact found two possible solutions. So our first one, our u1, is e to the minus 3t, that's a solution. And u2, which is e to the minus 1t, which is at minus t, are both solutions. So that's pretty nice. Actually, we were just looking for one, but now we've found two. But it's actually going to turn out even more than two. We have in fact found infinitely many solutions. Why? Because if we take any linear combination of these two solutions, that is also going to be a solution. Okay, and why? Because this thing over here is linear. So this is linear. And that means that if we put in any factor of this one over here, any multiple of e to the minus 3t, you can see that that will again be a solution. Similarly, if we put in any multiple of this, that will be a solution. And in fact, if we put in any sum of any multiple of those two, that's also going to be a solution. So we can let's just check that, because it sounds kind of crazy on the face of it. So in fact, any linear combination let's just check. So let's let u of t be some constant times u1 plus some constant times u2. Once again, do your differentiation thing, so you can double check this. And plug it back into the differential equation, and what you'll find is that with our new linear combination u of t, you should find that you get something like c1 times u1 in the form of the original differential equation plus c2 and u2's in the form of the original differential equation. You'll see what I mean if you work it out, and you're going to find that this term is equal to 0, this term is equal to 0, so the whole thing is equal to 0. So this is a fun thing to do for yourself. I've just kind of sketched it out, but prove to yourself that a u of this form, if u1 and u2 are both solutions, is also a solution. So what we're going to say is, if we want the most or a most general solution that we can possibly have, we will take this u over here, this linear combination. So we say that a general solution to our original harmonic oscillator equation is u of t equal to c1 e to the minus 3t plus c2 e to the minus t. And it's worth pausing at this point to say, does this make sense? We've found a solution that has two constants in it. And if you think back to integration, it absolutely makes sense, because when we've had a single derivative and integrated, we get one constant of integration. But when we have to integrate twice, which is what we have to do if we have a second derivative, we would end up with two constants of integration. So although the process that we've used we haven't actually done any integration, we have nonetheless equivalently had to integrate twice to find a solution to our second order differential equation. So it's not unsurprising that we end up with a solution that has two constants in it. Okay, so this gives us a general idea of how we're going to tackle any kind of second order linear constant coefficient homogeneous differential equation. We are going to posit a solution that looks like this, and then we're going to find the values of r which make it true. So this is going to be called our characteristic equation, and it's going to be the values of r that make it true that determine the form of our solution. So we've seen a form over here where our solution has decaying exponentials, but we're going to see solutions that have causes and sines, which might be a bit of a surprise, and combinations. But before we do that, I recommend that you take a bit of a break, make sure that you're happy with everything, go back and make sure that you're happy with the fact that a linear combination of solutions is also a solution, and then come back and we can look at the next bit of the course.